So what's the purpose of statistics?
Data-driven decisions.
What does that mean?
Like for trend.
And
With respect,
what does that mean?
it's about 95%. It's most likely going to happen. If it's over 5%, it's probably not going to happen.
Okay. So if it's over 95%, we say yes. If it's below 5%, we say no. What does that mean? What does it mean that something would have a 95 or a 5% chance of happening?
It means we expect them to happen or not expect them to happen.
But do we actually know what's going to happen?
Not for certain.
Not for certain. So in this process, when we say that we have certain expectations, we don't actually know what's going to happen. This is the cornerstone of correct statistical thinking. You don't actually know what's going on. Is that normal? Why not?
It's usually we know it's going to happen. Whether or not like day-to-day life or like an after school.
Do you know who's outside right now on the street?
But no.
Do you know how many cars are in the parking lot? Do you know how many branches are on this tree that I'm looking at? Do you know if there's somebody outside the door right now? So is it normal for us to not know what's going on? Yes. It is normal for us to not know what's going on.
Does anything ever have like 100% chance of happening versus never?
Great question. That's almost where I was going to go next. Are there things that have a 100% chance of happening?
The sun will rise tomorrow. The sun will set tonight.
Okay. Why would you say that such a thing is a 100% chance?
Because it's been happening for 4 billion years.
Except you actually don't know that. Someone told you it was 4 billion years. You haven't been around for 4 billion years. But a lot of people have told you that that's going to happen. Okay?
I would say that it's not 100% because it hasn't happened, so anything could happen, like the sun could explode tomorrow and then we would not see it rise.
You are correct. What are the chances that the sun's going to explode tomorrow?
Very slim, but it's not 0%.
Very slim, but it's not 0%. Okay. If I drop this marker, is it going to hit the table? How sure am I of that? Wow. Did. Okay. Do you think that there is a wad of chewing gum inside any of these computers in this room?
Probably not.
Probably not. So when we say, is there something that we would consider to be 100% certainty? On one level, we say no, because it's in the future, we don't know. But on another level, we say close enough. I'm not going to take apart all these computers in order to find a wad of chewing gum. That would not be reasonable, okay? So what we have here, when we talk about probability, we're talking about things that are not for sure or not certain. But there are two things that are involved here. These are philosophical concepts, and they are related. Operational certainty healthy skepticism. Certainty would say that yes, there are things that we can know for sure operationally, in other words, in practical terms. If I go out here and I'm going to cross the street and there's a car which is approaching me, I'm not going to walk out in front of the car thinking, well, maybe there'll be an earthquake and that car will flip over and I won't get hit. No, I'm pretty certain that car is going to keep going. However, if I see a car at a stoplight and I'm a pedestrian and I walk in front of that car, I'm pretty sure they're not going to run me over, okay? They could, certainly, but I'm pretty sure they're not. I'm operationally certain that things happen in a certain way, and I live my life that way. I walk out in front of cars constantly when they are stopped. And I assume that they see me and they're not going to run over me just for spite. Or for any other reason. I don't know their motives. But they're not going to run over me, okay? But healthy skepticism says, are there things for which we are absolutely not certain? Well, you know what? If I come up to a four-way stop and it's my turn, I don't necessarily just take my turn. I'm going to be kind of aware of the fact that other people might not think it's my turn, and they might run into me. So I'm going to kind of go through the intersection gently. I'm not just going to gun my way through and hope everybody makes room for me. If I'm a pedestrian, I'm walking across some crosswalk. It's not a good idea for me to always say they can stop, because maybe they can't. If I see a car traveling at a high rate of speed and there's a bunch of ice on the street, not a good idea to walk out in front of that person. I have healthy skepticism of their ability to stop. And it's healthy, okay? But what I like to tell the story is of my daughter, who, when there was a car 2 blocks down, she would not cross the street because I had said to her, if a car is coming, you should not cross the street. Well, healthy skepticism says, well, or I should say operational certainty says, they're 3 blocks away, it doesn't matter, I can go ahead and cross. So the balance between these two things says there are things that we know to enough certainty for us to be able to operate. And then there are things that we don't know, and we should consider the possibility that we don't know. So there are situations where we don't know what's going to happen, and it's good for us to keep that in mind. I don't actually know what's going to happen. But I'm not going to live my life thinking the sun might blow up at any moment. It just doesn't seem reasonable. But I am going to live my life thinking we could have a natural disaster where I'm not going to have power in my house for 2 weeks. That could happen. And so I'm skeptical that every time I walk into my house that the electricity is going to be on. That's healthy. It's healthy for me to make provision for the fact that there might be a power outage, for example. Now, that being said, okay, we do have this question about something happening by chance. Is it possible that something can happen by chance, or is it not possible that things happen by chance? It's very kind of interesting that when I went to church this past Sunday, that the pastor's sermon was basically about this. Kind of interesting, but here we are. There are some options here. One of which would be that there is a divine will that causes everything to happen. And so there's nothing left to chance. There's no such thing as a random event. Everything is predetermined and already written ahead of time. There's also other religious viewpoints, or quasi-religious, that would be karma or fate or something like that, where, you know, if you kick your dog in the morning, you'll have a car accident at night, something like that. There's also a scientific view which says that everything is based on physics and chemistry, and so your very existence is just basically an extended chemical reaction, and the things that happen in your life are just manifestations of certain natural laws of chemical behavior. Interesting those things may be, however, they don't really get to our situation, because what we're talking about when we're dealing with these questions of probability is, can we actually know what's going to happen? I want to know what to expect. Well, the fact of the matter is, there is no chemistry in the world that can tell me what I'm going to have for supper tonight, or all these other things. And it may be true that there's a divine plan that covers every possible eventuality, but it's also true that in religions around the world, we don't have access to that information. It's not like God gives me an agenda ahead of time and says, okay, these are all the things that are going to happen to you. We as human beings, we're limited. We don't know those things. And so in terms of operation, or in terms of functionality, we do operate on the basis of things happening by chance. Now, there are people who say that doesn't matter, and so you should deal with things on some other level. But for us, specifically, when we're looking at certain events that are happening, we're going to use at least the concept or the possibility that things do happen by chance, and consider what that means in terms of our results. So that we would say something like, if I give 500 people a certain kind of medicine, and 400 of them actually get better from a condition, and there's 500 other people I didn't give the medicine and none of them got better, it seems to me like there's something going on here, and it's most likely not by chance that this group got better and this group did not. But there's all kinds of thinking that goes on behind that, but at least for our purposes, we're going to consider the possibility that things do happen by chance and what that means, and that we can see some patterns in the way things operate, and that those are instructive and helpful to us, so that we can learn from things that happen in the world, and we see them operating in terms of our observations. We see the world happening in ways that look like they are by chance, and so we're going to go with that as an option. If there's some other thing that might determine everything else, we don't know what that is, and it's not actually functioning to tell us everything about what's going on. All right. So then, there are three types of probability that we want to consider. The first one is called classical or theoretical. The second is called observed or empirical. And the third is called subjective or experiential. So what's going on with these different things? With classical probability, what we assume is that every outcome is equally likely. So if you roll the standard die, you would have 6 different options, and they are all equal to each other. There's also then the idea, there are certain situations where we say, that doesn't make sense. It doesn't make sense for us to treat everything as like just a flip of a card or flip of a coin or a roulette wheel or a raffle ticket or something. When we do observed or empirical probability, then we're observing categories. And this goes back to our idea that we had, which is relative frequency. So I will look at a group of people and I will say, how many of them get the flu? Or how many of them watch NBA basketball? And so I'm just looking at a group of people and I'm getting a particular category, and the relative frequency of that is what I observe, okay? And then the subjective or the experiential is just like what it says. It's based on personal experience. Or I should say experience, because it might be your own experience or it could be the experience of other people. For example, we are all pretty well convinced that tomorrow is going to be very cold, because a lot of other people who have experience in forecasting things of this nature have told us that it's going to be really cold. Now, hopefully, you all are aware that if you're going to predict the weather, you're not going to be right all the time. But certainly, if you have certain indications that a certain thing is going to happen, then it makes sense to go with the experience, the voices of experience that are out there. So if somebody says, you know, if you don't get enough sleep, it's going to affect your immune system and you might get sick more often. Well, that just seems to be reasonable, okay? Or, you know, if you're not careful when you walk around out there, you might fall down and hurt yourself. Okay. Well, I've had experiences of icy walks where I'd fallen down and gotten hurt. So I'm more careful because I know that that happens. Okay? Now, in all three of these situations, though, we really need to describe what are we talking about when we say probability. What mathematical thing are we dealing with? And so if we want to say the formula for probability, probability is the number of items in a specific set divided by the total number. So if we're working with the idea of classical probability, then we would say, all right, how many different outcomes are there? How many different things can happen? And then how many of them are we interested in? Now, the way that this is done is by using the notation which is based on functions. So if you had some experience with functions in mathematics, you know how this works. If I want to know, if I have a standard die, what's the probability of getting a 5 on a standard die? Can somebody tell me what that answer is?
0.16%.
Not quite.
167.
It's 1/6.
How did you get that number?
Divided by 1.6.
Okay, so it's 1/6. All right. So if we write it as a fraction, it would be 1/6. What would it be if we did it as a decimal?
0.166.
Okay, it would be 0.16 repeating. at some point, if we want to round that off, we'd have to make it into a 7, right? So if I went, for example, to 3 decimal places, this would be 0.167 approximately. What percent is that?
16.7.
16.7, and if we rounded that off, it would be about 17%. So, probabilities can be expressed any one of these 3 ways: fractions, decimals, or percent. In the textbook homework, you'll need to see what they want, okay? And you do need to be careful to not round off too much as you go through the process. You will want to keep all your calculations, and then at the end of the problem is when you round off, okay? Because if you round off too soon, then that means your answer at the end will not have enough accuracy. So based on what the problem says, if they say use or round to the hundredths place or the thousandths place, what they mean is do the entire problem and then round off at the end. Okay, that's how it's supposed to work. So then we have either a fraction, a decimal, or a percent. And as you can see, what we're considering is that you have 6 possible things that can happen, and one of those would be the number 5. So this is not the letter P multiplied by the number 5. This 5 is a label saying what the thing is. So for example, if you flip a coin, it would be the probability of heads. Okay, this is just a label on the probability to tell us what we're talking about, which we normally consider to be 1/2 or 50%. There are people who actually practice flipping coins so that they know more about what they're going to get when they flip them. So don't hang around those people, and certainly don't bet on their coin flipping abilities. But that's something that can happen. Now, this is the same thing that happens for observed probability. Observed probability, we take the total number of observations, that would be on the bottom, and then the ones in that category would be on the top. And so then what we're basically saying is, for example, if I just took the people in this room and I said, okay, how many of you ate breakfast? Then you'd tell me. And then I would say, okay, that out of the total, that would be the chance of me randomly picking someone who had eaten breakfast. So let's say it's 90%. Then I would say I have a 90% chance, if I'm randomly choosing someone, of getting someone who has that characteristic. So there are similar ideas that I'm treating you all equally, but the number that I start with, I get by observation. I just see how many people are in the category divided by the total. And that's the same idea for relative frequency. So then that goes back to the same thing we talked about, the 5% versus the 95%. If I observe that 5% of people have a certain value for their blood pressure, then I would think that's going to be generally true, okay? So then a lot of times we take our observed empirical things and we think that they happen in every situation. And so we think that empirical ones are the same as classical ones. But they're not exactly the same, okay? They're not always exactly the same. We do have, though, something called the law of large numbers. And here is this. What is the law of large numbers? What that means is the observed probability should approach the theoretical probability as we have large numbers. Theoretically. So you roll one of your dice. You get a 5. You roll it again. Well, you might get a different number. You might get a 5. But if you roll it 600 times, you would not expect to get a 5 600 times. You would expect to get a 5 maybe somewhere around 100. It could be less or it could be more. But you would expect, as you do something over and over again, that the observed probability will get close to the theoretical probability. So this is the basic idea behind using large numbers of people when you're trying to study something. Then you think that if you have large numbers of people, that will relate to getting closer to the real value. And we'll see how that works down the road. What would be our minimum or maximum probability values? What's the smallest possible number for probability?
0.
0. What's the largest possible?
1.
1. Okay. So probability will be between 0 and 1 inclusive. So if you come up with an answer on a question and your probability is somewhere out of this range, then there's something wrong. Now, like we've said before though, just because we get a 0 does not necessarily mean it's impossible. And just because we get a 1 does not mean it's necessarily certain. But in terms of being operational and pragmatic about things, yeah, if it's 0, we pretty much don't expect it to happen. All right. So then, what if I have something, let's say I have probability of snow is 40%. What's the probability of not having snow?
60.
Why?
Because 100 minus 40 is 60.
Why did you do that though?
Because probability equals 1.
Why do you say that?
That you just told me.
No, I said the probability, the highest probability possible is 1. But I did not say that this necessarily plus that would be equal to 1. It is, however. Why?
It's either gonna snow or it's not gonna snow.
Right, because we assume that either it snows or it doesn't. And so then that must be the only 2 possible options. So therefore, those total probabilities must include everything. So then, yes, they have to equal 1. Now, of course, you have to ask the question, how do you define what you mean by snowing? But as soon as you do anything to actually define what that means, as soon as you define it, then you know what the opposite is. It's not that thing. So in most situations, we assume that either something is or it isn't. And so therefore we can do this. So we have 40%, 60%, and of course we recognize that 100% is the same thing as 1. So then we can make that work. This thing here is called the complement. The E complement. Because it completes the other one. All right, so this right here, what I've been going through here, these are all very general descriptions of how probability works and what it means. But now we're going to talk about 2 different methods of establishing probability. One of them is the tree diagram. And another one is a table of values. These are two different situations. And what we're talking about here now is, in a sense, formulas for how we understand how probability works. So, let's say that I flip a coin and I roll a die. How can I show graphically what happens here? And what I'm going to do is use a tree diagram where each choice multiplies the options. So I'm going to flip a coin, which would be heads or tails. And then if I roll a die, that means that I have 6 options on each of these. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now if I ask the question, how many possible outcomes are there? There would be 12. And what happens then is I take 2, multiply it by 6. To tell me that there are 12 outcomes. So this is pretty common, where we say, I'm going to describe a situation. I have this particular choice. It has this many options. And then I'm going to make another choice, which also has a set of options. And I can even keep going. How many different choices there are. And each time I choose, I'm going to be multiplying the number of options. All right, so let's go to, let's say, the union market. And I'm going to get a sandwich, a drink, and a snack. And I'm not going over to the place where they grill your own sandwiches. I'm just going to get one that's already been made. And I want to get a sandwich, and then I want a drink, and then I want a snack. If you've been to the union market, how many kinds of ready-made sandwiches do you think they have? 4? Okay. How many different kinds of drinks do they have at the union market? Assuming you've been there and you've looked around.
Maybe 10, 15.
Okay. You have all the different soda choices, right? You also have different juice choices. You have different kinds of milk. You've got different energy drinks.
20.
Let's say 20. How many snack options do you have? How many different kinds of snacks are available at the union market? Dalton, what do you say? Yeah, it's not a sandwich, it's not a drink. Right? It's all the baked goods. Okay, there's all kinds of chips, right? There's other little snack things that are in the cold part. Let's go 30. Okay. So you're going to walk into the union market, you're going to get a sandwich, you're going to get a drink, and you're going to get a snack. How many total options are there available to you? You multiply those numbers together. You come up with 2,400. Now, I've had some family members that had various mental health issues, including anxiety. And sometimes people with these kinds of issues, when they get into that situation, they think they actually have to pick the right choice. Because you have to have the correct drink that goes with the correct snack and the correct sandwich in order for it to be optimal. And so they would have to go through all 2,400 different choices and evaluate them in order to be able to buy something. Most people don't do that, right? Most people, they just walk in and say, oh, I like this, I'll just get it. They don't say, well, you know, if I get the Coke versus the Sprite, how would that go with the Sun Chips and the different flavors? Which one would actually be optimal? Nobody does that, or hardly. So you can see how when you start multiplying choices, it actually gets pretty crazy. Okay. Now, let's say that you have a deck of cards. And you're going to pick one of those cards at random. How many options do you have? Can somebody tell me how many cards there are?
52.
52. Then after you get that card, the next one would be 51, right? Because there's 51 options for that. So I want to take 52 times 51 times 50 times 49 all the way down. Can anybody tell me what is the mathematical notation for that? I'm sorry, what did you say, Alyssa? No, it's not. This is called factorial. It's 52 with an exclamation point after it. All right, so maybe you've got that button on your calculator. Do you have such a thing? 52 factorial. You might have to check your owner's manual or something.
Yeah.
Okay, what do you got for a number, Chelsea?
Pops up as super low number. It's 8.06 to the 67th power.
8.06 times 10 to the 67th power. Okay? What this means is, if you shuffle a deck of cards, and there's an interesting bit by Stephen Fry on YouTube. If you shuffle a deck of cards, there has never been that combination of cards in the history of humanity. Because if you shuffled cards and you came up with different decks with different orders of cards, it's impossible for you to do that and end up with the history of humankind, because this is such a high number. So things really get out of hand once you start thinking about how many different ways can a certain thing happen. You start multiplying the different options, it gets really big. So normally with a tree diagram, we don't go that crazy with stuff. But it is true that, for example, let's say you have 10 light bulbs and 3 are bad. And I'm going to take out 2. So what does that look like? Well, I could make a tree diagram with 10 different things and label 3 of them bad and 7 of them good. But I'm not going to do that. I'm just going to write it like this. 3 bad, 7 good. This would be what happens if I'm going to take out one of those light bulbs. But then what happens when I take one out? It changes the situation. What happens if I take out a bad light bulb? What am I left with?
Two that are bad and seven good.
Okay, so I have 2 bad, and here is still 7 good. What if I take out a good one?
You have 3 bad and 6 good.
3 bad and 6 good. Now remember, this is like 3 branches and 10 or 7 branches down here. You don't see all the branches. But when we look at this and we say, I'm going to multiply the number of options. I'm going to multiply to see what's going to happen here. So if I have 3 bad ones to start with, and I take one out, then how many options are there for me to have both of them come out bad? And the answer is 3 times 2, or 6. So I have 6 possible options where the first one would be bad and the second one is also bad. Once again, I'm not writing down all the different pieces of the tree, but there are 3 branches here, and then on those 3 branches, each one has 9, 2 of which are bad and 7 are good. So I multiply as I go. Well, what about the bad and then the good? Again, I'm going to multiply, so that's 3 times 7, which is 21. And then this is something that people don't normally think about, and that is if you change the order of how things happen, it's actually a different experience. It's a different thing. So if I get a good one and then I get a bad one, that's a different option than doing it this way, bad and then good. The number of options comes out to be the same, 7 times 3 is 21, but bad, then good is different from good and then bad. When I'm making a list of the possibilities, the order is important. Okay? And then what about this? Well, this would be 7 times 6, which is 42. That's how many good things. Now, most people don't think like this. Most people don't have to deal with this. So you might have to practice this a little bit to feel comfortable. But this is how it works, okay, in terms of writing down the number of options. But we don't necessarily just want number of options, right? We want probabilities. We want to know what is likely to happen here. And so when we see that this is 10 options here, there are a total of 10 options here. Each of these things has 9 options, so that's 10 times 9. This would give me then 90 total options. And as it turns out, if I add these numbers together, I do get 90. So I had 10 light bulbs. I take one out. I now have 9 light bulbs. So 10 times 9 is 90 options. So I can look at these now as probabilities instead of just looking at these as numbers of options. So this would be 3 over 10, 7 over 10. This is 2 over 9, 7 over 9. 3 over 9, 6 over 9. So now what happens when I think about my probabilities? Every option that I do here, I'm going to be multiplying the probabilities. So what are the chances that I have both bad light bulbs? It would be 3 over 10 multiplied by 2 over 9. because I multiply on top to get my number of things, my number of bad options, and then 10 times 9 is the total number of options. Well, that's just multiplying this probability times this one. So that would come out to be a number, I think 1 out of 15, which is approximately 7%. So when you're doing a tree diagram and you're looking at how to put probabilities together, as you go from one thing to the next, as you go down the tree, you're multiplying the options, then you're multiplying probabilities. So this idea would be bad and bad. The first one is bad and the second one is bad. So you will see this in your textbook. The probability of A and B is the probability of A multiplied by the probability of B. That works if it's a situation like this, like a tree diagram, where you're going from one step to the next, and you multiply the number of options, you also multiply the probabilities. Okay. Now, what if I want to say, what's the probability of getting one, or exactly one, bad bulb? If I consider the probability of getting exactly one bad bulb, there are different ways that can happen, right? It could be that it was the first one, or it could be that it was this one. So if I say, how many options do I have here for getting exactly one bad bulb, I would add those numbers together. So it would be 42, again, out of 90. So this would be 42 out of 90. I'm not going to worry about what that number is, as long as you understand. So then, in the textbook, once again, we have this statement. The probability of A or B is the probability of A plus probability. So again, we're making a connection between the situations that we see and the mathematical relationship. If I have options which are inclusive, it could happen this way or this way, then I'm going to add those probabilities together, and that's how I figure out the idea of or inclusive. It could be this or this. That means I have to add those probabilities together. All right, now your textbook goes through more. The PowerPoint presentations I have out there go through more detail. But what I want to do is to go to this idea of the table of values so that you can see the difference in how this works. And I want to double check and make sure that my video is going to be all right with this. I want to go over to about here. All right, so I'm fine. So what happens with the table of values is that I am going to take a group and I'm going to separate it into different categories. So let's say that I've got nursing students and business students. And I'm going to have them like either Coke or Pepsi or Coke. And I'm going to just drop some numbers in here and make them up. All right, so here I've just made up numbers and I've just dropped them in here. And I say, all right, what's happening with this? If I ask the question, what's the probability of someone being a Coke drinker or liking Coke? Well, it could be nursing or business students, right? So I would add those things together and I would take it out of the total. So this would be 50. And then how many total do I have here? I'm sorry? 180. So, well, let's change it to make it easier. No, I guess I'll stay with that. So Coke is going to be 50 out of 180. This is 80, this is 50, this is 60, and 21. Okay. What would be the probability of being a nursing student?
60 out of 180.
60 out of 180. Yep. So again, we're just adding these things together, all right? But once we get to the idea of and, what's the probability of being a nursing student and a person who likes Coke? In this situation, we are no longer going to use a mathematical formula to figure this out. We're simply going to look at the definition of and, which means they are both true at the same time. So if I look at this right here, how many nursing students also like Coca-Cola? 10. And so I'm going to say this probability is 10 divided by 180. And as it turns out, if you do the math, this is not the same thing as multiplying these two numbers together. So this idea, when you have a table of values and you say, I want to know what this probability is using the word and, this is actually called the intersection. It is the place where those two things overlap. They are nursing and they like Coke. That's 10 people out of the total 180. Then we have the question, what about the word or? If we say nursing or Coca-Cola, well, we want to include everybody that's in nursing. We also want to include everybody that likes Coca-Cola. So how does that work? If I include all the nursing, I include all the Coke drinkers, how many people is that? It's 100. It's the 60 nursing people plus the 50 business students, but that would double count that 10 in there. So then I would subtract the 10. And once again, that would be over 180. So when I have a table of values, then it's the probability of nursing plus the probability of the Coke drinkers minus the intersection. This formula is also in your textbook, okay? So when you look at the word or, talking about a table of values, you include everybody, but you make sure you don't double count. That's what this formula does right here, which is different from what we had in the first part. When we said or for that first situation, we just added the probabilities together. But here, it's a bit more complicated. All right, so this is hopefully all the information that you need in order to do that next homework assignment. Certainly, if you have any questions, let me know. And then that will be due Thursday. And then coming up next week, we'll talk about the rest of Chapter 5 and the next homework assignment. All right, so I hope you have a good day. Hope you stay warm. And we'll go from there.
So 4 is going to be due on Thursday.
That's correct.